So we already talked about this collection of vectors can be understood as matrices. So sometimes you collect multiple column vectors like this. This is going to be a matrix. Sometimes you can collect a row vectors like this, where this can form a matrix as well. And well, in this sense, vectors and matrices are connected, and actually lots of operations are connected as well. Well, anyhow, given a matrix, where this direction is called as a row, this direction called as a column, and tensor is some kind of generalized notion. So you may heard of the vocabulary tensor, and this is well, sort of like array for us. So one-dimensional tensor is scalar, and well, zero-dimensional tensor is scalar, and one-dimensional tensor is vector, two-dimensional tensor is matrix, and there is a k-dimensional tensor that could be just tensor, and their visualization is given like this. So if you come up with this vocabulary tensor, well, you don't need to be afraid. And here are some basic operation. So matrix A, well, lots of elements in it. Matrix B, well, lots of elements in it. Important thing is their size are the same. So both of them are m by n matrix. And here comes the addition. So where you take the element at the same position and take the summation. Subtraction, take the element on the same position and the subtraction. With scalar multiplication, you put a scalar value in front of the matrix, and this value goes to the element. So basically, you're distributing the same scalar value for every member of your matrix. And you can come up with some combination of scalar multiplication and addition. So Ka and Lb is simple. So Ka and Lb. And matrix multiplication. So you have two matrices. In this case, you're going to take each row of the first matrix, and you also take each column of the second matrix, and take the inner product between them. And the result goes to the index of the row and column. So this is something you are familiar with. So A is something like this, B is something like this. We'll take the multiplication of A and B. So that is going to be, for example, 2 is 1 multiplied by 0, 2 multiplied by 1, and 3 multiplied by 0, and so on. And 3. So, well, you can easily do this to come up with matrix multiplication. Well, one of the important thing is the order of the multiplication methods. So, well, one other thing is dimensionality important in this matrix multiplication. So, in this case, well, multiplication of BA is not defined because neighboring dimensions are not matching. So, well, this is something you should be familiar. Well, there is one not as common as the inner product, but well, these days people use this kind of sort of special multiplication a lot as well. So this is an element-wise multiplication. So you have given two different matrices, and this circle dot is element-wise multiplication. So you take the multiplication of 2 and 2, and that goes to the element on coordinate 1, 1. And 7, 8, that's going to be 1, 2, and so on. Well, this is not correct. And here comes some additional operators that are quite straightforward. So there is operator transpose. So you take the diagonal and sort of mirror them. So these two switch their position, where this goes 2 over here, this goes 2 over here. So eventually you're going to have well, this matrix in different directions. So initially you have 3 by 2 matrix. After you take the transpose, you have 2 by 3 matrix. And the elements, they are changing the location. So ij becomes ji, and since transpose is actually mirroring of something against the diagonal, so A transpose, well, transpose of A transpose A is A itself. And AB transpose is equivalent to B transpose and A transpose. And A plus B transpose is equivalent to A transpose plus B transpose. Which is just some simple properties. And trace is where you go along with the diagonal line and take the sum of all those elements. That's the idea of a trace. And rank is something important, and this is relevant to the QR decomposition. So R over here, well, this R matrix is highlighting the length of the matrix. So the idea of length is the number of linearly independent column for row. And from here, where we can come up with a special notion, so for a square matrix, so n by n, so number of column and number of rows are the same, where we can say a square matrix is a full length. That means where the matrix is invertible, and the matrix is also non-singular, and also that means it has a determinant that is not zero. And here comes the identity matrix. So where this is n by n matrix contains 1 on the diagonal and 0 everywhere else. So basically on the diagonal, it has 1 and everything else is 0. And inverse matrix, this is one of the most important concepts in the linear algebra, where we just define the identity matrix. And for a given matrix A, if you multiply another matrix that results in the identity matrix, in that case, we say this matrix that we just multiplied is inverse matrix of A. So inverse matrix definition, where given matrix, if you multiply the inverse, then you're going to have the identity. If you have multiplication of the matrix and take the inverse of them, then you're switching the order and taking their inverses. And A transpose inverse is the same as A inverse transpose. And just for note, where A plus B inverse is not equivalent to A inverse plus B inverse. And this is a sort of intense form, but we are going to see this in eigenvalue decomposition. Well, computing inverse matrix is again straightforward. So if you took linear algebra, well, this is one of the common problem for your first midterm or first quiz. So I'm sure that you know how to do it. So you first take the determinant of the matrix, and where you take 1 over the determinant, and basically you switch the position of A and D and change the sign of B and C. Based on the value of determinant, where we can say a matrix has inverse or not. So in order to have an inverse, you need to have the determinant value non-zero. And we limited our discussion for 2 by 2 matrices only, but well, you can also come up with 3 by 3 matrix. So the determinant for 3 by 3 matrix is computed like this. And you can even generalize it for n by n matrix. So you can come up with this formula for n by n matrix. And here's some kind of a trick that you can use for computing determinants. So take a look. Now let's start our discussion from where application of inverse matrix and also matrix as a linear transformation. So if you apply the idea of inverse matrix, you can easily come up with a solution to system of linear equation. So basically we can write down a system of linear equation in a generalized format. So where you have multiple unknowns, x1 to xn. And for each of the combination to the set of coefficient, so A, ij, and each of these equation has a result which is y. So given that the same idea can be notated using matrix. So you have a coefficient matrix, and here is a set of unknown, so unknown vector. And here comes your output. Given that, well, if I notate this into a coefficient matrix and unknown vector and output vector, so where we can write down a matrix multiplication AXY, which represent the same thing as the above system of linear equation, where I want to multiply A inverse in front of both sides. So where something like this, and this guy becomes identity matrix. So identity matrix multiplied by another matrix is where the another matrix again. So where your solution to the unknowns becomes where each matrix multiplication A inverse multiplied by Y. So here comes an example. Given these two equations, where you can easily come up with the coefficient matrix A and output matrix Y. And AX equal Y becomes AX equals A inverse multiplied by Y. So if you calculate the inverse of the coefficient matrix, you can come up with this matrix and multiply it to the output matrix, and you can easily come up with the unknown value. So this is your solution. So make sure you understand the concept between where basically this is switching. So system of linear equation to where matrix complication, and we are multiplying the inverse matrix to both sides, things like that. Well, this same pattern of the operation will come back when we study the linear model. So we are going to study logistic regression and linear regression. When we study that, we will see almost a similar form to derive the algorithm. So this is what I just mentioned. So just take a look. So when we talk about linear regression or logistic regression, where it's going to be, so the coefficient matrix becomes data, and the unknowns will become the weight of the model or the model representation itself. And the output becomes the target output. So given D, we want to learn some kind of a prediction model that transforms the original data to the output. So we are going to study this function fx that transform D into Y.